the sensitivity analysis. You're going to talk to us. And okay, this one.
Yes, come boy.
Good morning to everybody. I'm Maria Gamba Perez from Complutense University of Madrid, and this is a joint research work of Maria Jesus López Herrero and me. The talk is organized as follows. First, I'm going to introduce the theme. Next, I'm going to describe the stochastic SVIS model. Following, I will define two random variables that quantify the potential transmission of an epidemic. Following, a sensitivity analysis is derived. Numerical results, conclusion, and bibliography is at the end of the talk. We describe the evolution of an epidemic process under a stochastic approach. This approach is preferable under small communities and when we want to take into account the specific characteristics of an infectious diseases or the population. We extend the classical SIS type model, but including vaccination as a health control measure. In addition, this vaccine is imperfect. Moreover, infections can be produced by an external source of infection. So this is the main difference to the classical model. We quantify the potential transmission of an epidemic, analyzing the exact reproduction numbers, E0 and RP. To describe this model, we consider infectious diseases that don't confer permanent immunity. In this sense, individuals, when they are recovered from the disease, are susceptible to get the infectious disease again. We consider constant and moderate-sized populations where individuals are homogeneous and are uniformly mixed. In this sense, they present the same characteristics to get infected and to recover from the disease. Population is not isolated, so always there is a reintroduction of the disease. Prior to the start of the epidemic, a percentage of the population is vaccinated against the disease by a vaccine. This vaccine is imperfect in the sense that individuals that have been previously vaccinated could be infected. We don't consider revaccination of the population. So when an infected individual is recovered, they are susceptible again and never will become vaccinated. These are the model parameters. So N is the population size, the internal transmission rate beta, external transmission rate is T, vaccine probability failure is 8, and recovery rate is gamma. We describe the evolution of the epidemic process in terms of this bidimensional continuous time Markov chain, where VT describes the number of vaccinated individuals at time t, IT is the number of infected individuals at time t, and as the population have a contact site, we can obtain the number of susceptible individuals from this equation. Here we can see the outgoing transitions and rate from a generic state. And here are the rates. We can see that this rate is not linear. So this is complicated to derive the theoretical result and to compute all the characteristics. To solve this inconvenience, we organize the state space of the Markov chains according by levels. This organization permits us to study the continuous time Markov chains as a quasi-birth process. We can see that there is an absorbing set of states that is when there is not vaccinated individuals in the population. To quantify the potential transmission of an infection process, we define it in the reference number 1, the exact reproduction number RE0 and RP. The exact reproduction number is the exact number of secondary cases produced by the typical infective individual during its entire infectious period. In contrast, RP, the population reproduction number, is the exact number of secondary causes produced by all currently infected individuals in the population prior to the first recovery. Now I'm going to explain the main difference between the classical quantifiers, basic and control reproduction numbers, versus our statistical reproduction numbers. The main difference is that the classicals are deterministic quantifiers. In a stochastic frameworks, the exact reproduction numbers are preferable, in the sense that these characteristics, random variables, give a real measurement of disease spread, in the sense that they don't count contact to individuals previously infected. In this sense, they aren't an overestimation of the population infected. In addition, the exact reproduction numbers can be defined at all times, and not only in the time of invasion, as the basic reproduction number does. In addition, these measures are random variables, so we can have more information about these variables. Now I'm going to conduct a sensitivity analysis of these variables. The sensitivity analysis is relevant in the modeling of epidemics, particularly when the model parameters are estimated from a given data set. This methodology allows researchers to assess the robustness of their model, ensuring that it provides accurate and reliable insight into the spread and control of infectious diseases. Our interest is to quantify how long small variation in its model parameter can affect in mathematical epidemiology model output. We evaluate the importance and the influence of each model parameter in the expression of an epidemic process. The perturbation analysis will be conducted for a factorial movement of both variables. In the reference number 1, we computed all the factorial moments, and the factorial moments, we gave this notation. And in this study, we continue with this notation. To approach the perturbation problem, we need to compute the derivatives and elasticities of the expected values and standard deviations. The elasticity of a general random variable is defined as follows, and to address this study, we need to derive all the expression that in the reference number 1 we obtained. We know that, I say to you now, that we have 4 parameters, so we need to take derivatives of the factorial moments respect to the whole set of the model parameters. In when we obtain the following equation, so now we introduce the following notation to take derivatives of this in this expression. Taking derivatives in equation 2 respect to its single parameter of the model and keeping the other constant, we obtain the following theorem that involves both factorial moments and its derivatives, conditioned to a generic state for the Markov chain. As we see in the theorem, we can obtain all the moments of this random variable recursively. This algorithm shows how to proceed to compute the related derivatives in an ordered, in an efficient way, starting from k equal to 0 in natural order for all the number of vaccinated individuals. After that, applying elasticity definition in equation 1, the elasticities for the mean and standard deviation of the exact reproduction number conditioned to any state of the Markov chain respect to each model parameter are given by this expression. For the random variable population exact reproduction number, we applied an analogous methodology and we compute the first derivative of the population reproduction number using the following theorem. Again, we obtain a recursively equations for any order and any level of vaccinated individuals. We compute factorial moment of the related random variable with the help of algorithm 2. Elasticities for any number of vaccinated individuals are computed from this expression. Now I'm going to give you some numerical results. The aim of this section is to study the relative importance of the model parameter for a particular sample for transmission of diphtheria virus. For all experiments, we consider a population of 100 individuals where prior the start of epidemic, a percentage of the population has received a vaccine to prevent infection. The epidemic is detected as soon as the first case of infection is produced. So this is the initial state. The parameters are as follows according to the information presented in reference 2 and 3. As we can see, for these infectious diseases, when the coverage is small, only the 20% of individuals vaccinated, we can see that the most relevant parameter is beta. And in contrast, when we consider the population reproduction number, we can see that gamma is more relevant. When we consider a large vaccine coverage rate, we have the same behavior in both random variables. We perform the sensitive analysis via derivatives and elasticities. These quantities are obtained with the help of the algorithm 1 and 2, which were implemented in our software. Our numerical algorithms provide results depending strongly on the population size and the other parameters of the model. The average time to execute algorithm 1 for a population are as follows, and for algorithm 2 are this. Results can be used to help institutional authorities to identify the most effective prevention control health strategies, such as vaccination campaigns, social distancing measures, or contact tracing efforts. This is some bibliography. Thank you.
modern theme that you presented us. Do we have any questions from the audience or the? Huh?
Also, we have the
Yes.
What?
We have the virtual link. I don't know.
Ah, okay.
Yes.
Maybe.
No, it's okay. It's okay.
No, no,
Ah.
it's all set.
Yeah. It's okay. It's fine.
Okay. So we'll move to
Thank you for your
Thank you.
presentation.
to the next presenter, please. Yes, David Medina, and he's going to present us about learning machines in what?
It's different.
Okay.
Yes.
Just a second, I'll share the presentation. Here you are.
Please.
Thanks a lot. Okay. Hi, everyone. Nice to meet you. My name is David Medina, and I'm doctor from University of Magallanes in Punta Arenas, Chile. And I'm working on protein engineering and machine learning algorithms for developing proteins with desirable properties. And today, take about of how to use machine learning or how to explore machine learning algorithms and numerical representation strategies to predict models for protein networks. So here, for context, the proteins has different function and characteristic in specific for structural like cell structural or internal organization. In the case of the development, have transport or manufacturing, also has a functionality for maintenance, storage, and catalytic, but it's very important in catalytic like an enzymatic task, for example, for biotechnology, industrial, and pharmaceutical elements. For building a protein, it's necessary to have an amino acid, and the amino acid is the building block of the proteins. The union of different amino acids by peptide bonds create a peptide sequence that you can see here. And obviously, with this, it is called primary structure, and the union, you can see, for example, methionine has particular different residues. That the property of the residue is obtained by the side chain groups with different characteristics. There are 20 amino acids in the life. So folding of the protein is considered from the primary structure in here, and then the union of the different residues by hydrogen bond is created the secondary structure into type of folding like alpha and beta structure, and the union of the folding in different residues by weak interaction levels is create the tertiary structure, and the union of different tertiary structure create a quaternary structure, and you can see in this picture the create of the hemoglobin, that is a global transport for transport of the oxygen. And the problem that's in here that the protein not alone in the life, not alone in organism, and the protein has interaction with another proteins and has interaction with drugs or chemical compounds. And it's possible to see that in the real life that the proteins has interaction in metabolic pathways, the structural activity, and for example, it's possible to relate or to correlate these networks with a state of the people, for example, disease associated with Alzheimer, for example, and in more interesting, in my case, how it's possible to improve the interactions or improve the affinity between a protein with a more economical chemical compounds to create a new interactions. So the real problem is, okay, how it's possible to predict the affinity between some proteins because it's only a planar zone in the interface zone between two proteins. And in the case of chemical compounds, it's more complicated because it's only different zones in the 3D representation of the protein, but different bioinformatic tasks are related with this problem. Using dynamic simulation or molecular dynamics, docking also. But the problem is the computational cost in here, because when we have different simulations or different landscape analysis in here, it's necessary a lot of computational cost to cover all elements. For these machine learning applications, as an alternative to predict this type of task. And we want to obtain the task. It's possible to classify in different elements. For example, protein affinity prediction with the affinity with chemical compounds, with proteins, and with peptide that is very similar to proteins. And the use of machine learning algorithms requires how to represent the protein and the chemical compounds, and in this case, the interactions between these two molecules. For example, to represent chemical compounds, it's possible to use a string like a smile representation, give description or characteristic of this chemical compound, like atomic bonds, and also it's possible to use molecular representations by graph structure. In the case of protein and peptide ligands, it's possible to use a sequence like string, natural language processing, obviously, protein structures, graph structure, and 2D or 3D representation to create image and apply different architectures like convolutional neural networks. So the problem here is they are not an unique framework to predict or to create the affinity between a protein and chemical compounds or a protein of ligand. And for this, when use 3D structure information is necessary to obtain the crystal of the protein and the crystal of the chemical compounds, but is with AlphaFold right now is possible to predict, but it's a bit complicated if we want to obtain all landscape for the different elements. And but that we propose a sequence-based approach that is based on natural language processing methods, and in this case, we use different pre-trained models available in literature, like BIPRE, SN1B, Word2B, common offers for protein sequence. And in the case of chemical compounds, we use, for example, Word2B or Circuformer. And the idea is I have the chemical compound or the protein sequence, apply the encoders or the pre-trained model, obtain the numerical representations, then evaluate the latent space visualization, evaluate if there are initial separation between different functionality or different characteristic, and obtain the dataset, the coded dataset. So the problem is how to represent the complex structure, or in other case, the interactions between the protein or the chemical compounds of the protein. In this case, using only linear information, we try to represent this using three strategies. The first is the simplest, is based on the concatenation, because I have the protein, I have the chemical compound, I make a union and create a concatenated vector. And using the concatenated vector, we can apply PCA, or principal component analysis, to make linear combinations to represent a unique element, and a kernel PCA to make nonlinear combinations. So also in this project, we also try to develop a generalized pipeline to train predictive models, in particular for protein networks or for protein functionality tasks or for protein engineering tasks. The idea is I have the data set, I explore different machine learning algorithms with default hyperparameters and different architectures previously reported in literature based on different authors, and deep learning methods. And next steps, evaluate the performance. Then, with a statistical approach, obtain the best models based on the highest performance. And then this approach, these models, optimize the hyperparameters using genetic algorithms, and then combine all representations, all individual models in a unique big assembled learning model. With this, we explore in a field case study using the cytochrome P415. Sorry, the idea is, okay, how is possible to develop classification model for affinity between a chemical compound and protein, for the case for cytochrome in this case, and we evaluate different numerical representation strategies for proteins and different representation strategies for chemical compounds and the union of the different elements. So in this case, there are no difference between physicochemical properties and frequency space, but there are difference concerning appear difference concerning the natural language processing. But for example, appear the median in the case of supervector machine, or for example, gradient boost or random forest algorithms appear has better performance in comparison with other methods. Once we applied the optimization process, not only optimize the hyperparameters, also optimize how it's possible to combine the different algorithms individual to create an assembled learning for each numerical representation strategies. Obviously, the selected method. In this case, for the cytochrome, we obtained 6 best model, and we define different stages or different steps to optimize the individual model. For example, using fast text datasets, obtain an optimized model combining Gaussian night bias, multi-layer perceptron algorithms, and different stage normalized. So the idea, okay, is how to combine this individual model in a unique model, and for this we apply assembled learning, and then obtain a model with precision of 19%. That is very nice in comparison with the state of the art right now. But the idea is, okay, how to use the model. Because we can train a model, we can obtain the model, but the idea is how to use, because it's necessary to help to wet lab. And in this case, we explore different use for evaluate enzymes with a similar enzymes or a similar protein with different chemical compounds in here, and new enzymes with single permutation mates with 2 components. In the figure 8, you can see that they are the same enzymes. The model classify this as positive interaction, and this and this are negative interaction. And we validate the model using dynamic simulations or molecular dynamic simulations and obtain these metrics. This is a kilocalmole. And with this, highest negative value indicate a highest affinity with the model, and lowest affinity is related with the lowest negative values. So in this case, we can see that the model is okay, but in here, the model is failed because for this figure, the HPL present positive interactions, and the model has a positive interaction. But with fipronil, the model also give a negative interaction, but in the reality is a positive interaction. So it's necessary to improve how to represent the information. So as an alternative, also we explore protein complex interactions, and using different data sets reported in literature with different tasks. For example, the evaluation of kinetic constant between 2 complex structures, the evaluation of the affinity, or the evaluation of the free energy. We explore different deep learning. Also, the machine learning algorithms, we explore different deep learning architectures like graph convolution networks and CNN. The use of graph convolution in here is because we can represent the network as graph structure. Each node represents the protein, and the edges represent the affinity or the value that it wants necessarily to predict between two proteins. And for this, we explored, in this case, I can see the architecture of the 4 CNN architecture explored with different block pattern recognition blocks, learning, configuration, and optimization and loss function. The problem that is not a unique generalizable approach in here, because we want only a unique method, but with the 6 tags evaluated, there not appear a unique specific method to model or to predict, to create predictions. So in here, with the CNN methods appear be nice for free energy predictions. The machine learning algorithms appear be for kinetic constant, and a graph convolutional network method appears nice, a nice performance for affinity between 2 proteins. So, but the problem is in the how to represent or how to describe the elements, because there are not a consensus. And obviously, we have architectures, but we don't have a consensus to predict a unique method, a unique framework. So some conclusions or some discussion, they are not conclusion because it's a work in progress. We have developed a framework to predict protein ligand, the affinity, combining natural language processing representations and spatial transformations using genetic algorithms to optimize the performance of the method. And we generalize the predictions strategies for protein interaction network based on CNN or GCN, depending of the type of the task, if the affinity or if the free energy or if kinetic constant. And we are working in the create a large language model using the chemical compounds and the protein structure to create a strategy to unique representation based on all information reported in literature. Acknowledgements of the team and the institution, and for your attention. Thank you so much.
Artificial intelligence, learning machines, so combining with biology, of course. A lot of chemistry
Yes.
for us.
Chemistry, biology.
Do we have any questions? Or please?
Thank you for your presentation, and I was wondering, how many did you collect and input data sets for using a machine learning?
Yeah. Correct or correct?
Correct.
Correct.
Yeah.
Yeah. For correct data set, we used only validated reported literature, validated experimental, validated wet lab.
How many do you get? Do you get?
Create?
Do you get input data set? How many?
How many data sets?
Number examples.
Statistics.
Yeah. Depending of the task. In the task of cytochrome, we have 10,000. Yes. In the case of the sorry. This is the number in the case of the different protein networks. But right now we are working with the Inkscape and the string database, because the problem with this database, for example, is so big, but they are not a numeric value with the affinity. It's only binary. But if we want to obtain a numerical value, it's not possible.
Thank you very much. Okay. Now I call the next presenter, Mr. Daisuke Takahashi. Okay. I thought I pronounced okay. Your name. He will talk about multiple integer divisions with an invariant, dividend, and monotonically increasing or decreasing divisions. Please.
Thank you. Thank you for the lesson.
Coming.
So good morning, everyone. My name is Daisuke Takashi from University of Tsukuba, Japan. Today, I'd like to talk about the multiple integer divisions with an invariant dividend and monotonically increasing or decreasing divisors. So this is the outline of my talk. So integer division is a widely used arithmetic operation, so being included in many applications. So in general, division is known to be slower than addition, subtraction, and multiplication. For this reason, algorithms have been proposed to perform division using only addition, subtraction, and multiplication. So as for related works, so algorithms for division by invariant integers have been proposed by many researchers. And then algorithms for integer division using reciprocals have been proposed. And then 32 and 64-bit integer division using double precision floating point arithmetic have been proposed. So in this research, we consider multiple integer divisions when the dividend is invariant and the multiple divisors are monotonically increasing or decreasing. So this is a limited case, but such multiple integer divisions appear when converting an integer to Montgomery representation. Montgomery multiplication is used for crypt systems. So for multiple moduli. So, I cannot. Sorry. So the equation can be not shown in this environment. So an unsigned integer division is defined by the quotient and remainder. Q is A over B, where the dividend is A and the divisor is B. So we consider multiple integer divisions when the dividend is invariant and the multiple divisors are monotonically increasing or decreasing. So in such multiple integer divisions, we show that if the dividend and divisor satisfy a certain condition, then if only one question quotient is calculated by division first, the remaining quotients can be obtained by correcting the previously calculated quotient at most ones. So the unfortunately, so equation cannot be shown in this. Sorry.
Maybe try opening in PowerPoint. It's a little bit obvious now.
Sorry.
And maybe try opening the presentation with PowerPoint.
Okay. So.
If we open it in PowerPoint, it's not possible to do
Is there any problem? I mean,
Equations cannot be shown.
okay.
If we open it with PowerPoint, I'll show you. Because
This is for Libra.
yes.
So
Do you remember the problem of
yes,
yesterday
yes,
with PowerPoint?
yes,
So
yes.
just double tap.
I will do it.
This one,
No,
yes.
no.
You go individual row to see if there are.
Just skip it for now.
Yes, close it.
Close it. Okay. And yes. We were here, eh? No? Sorry. Here.
Okay.
Here.
Okay.
Just for the audience, the questions
that you have, we saw in the chat room, they're going to be answered at the end of the session. So please.
Thank you. So the unsigned integer division is defined by the quotient Q and the remainder R. So where the dividend is A and the divisor is B. So we in such multiple integer divisions, we show that if the dividend and divisor satisfy a certain condition, then if only one quotient is calculated by division first, the remaining quotient can be obtained by correcting the previously calculated quotient at most once. So this is a proposed algorithm. So we consider integers A and B and C. So if the condition, so then we have inequality 1. So proof is very easy. So for any real integer x, so the inequalities hold. So we have the inequality 2 and 3. So from inequalities 2 and 3, the condition for inequality 1 to hold can be obtained. So by using these inequalities, we have the quotient A over B can be obtained by making at most one correction to the quotient. So the theorem 1 is applicable when the divisors are monotonically decreasing. So when the divisors are monotonically increasing, the quotient can be obtained in the same way by reversing the order of the divisors. So this is algorithm for multiple integer divisions with an invariant dividend and monotonically increasing divisors. So if it's known in advance that the condition of theorem 1 is satisfied for the dividend A, the minimum divisor B0 and the maximum difference C between adjacent divisors, then multiple integer divisions can be efficiently calculated using the proposed algorithm. So the first and second lines of the proposed algorithm calculates the quotient Q n-1 and remainder n-1 for the dividend A and the divisor B n-1. In line 4, the previously calculated quotient Qi plus 1 is used as the approximate quotient. And in line 5, the remainder R1 is obtained from the dividend A, the divisor B, I, and the quotient Qi. If the remainder Ri is greater than Bi in line 6, so we correct the Qi and Ri. So we now consider vectorization of the proposed algorithm. So in the proposed algorithm, the quotients are obtained by correcting only one previously calculated quotient, and this process cannot be vectorized due to data dependency. So by simultaneously correcting multiple previously calculated quotients, this data dependency can be resolved. So as a result, making it possible to vectorize the process. So to avoid the data dependency, the previously calculated quotient for the divisors at multiples of the vector lengths are used as the approximate quotients. So the value of C in the proposed algorithm is the maximum difference between divisors at intervals of the vector length. So this is the vectorized multiple 64-bit unsigned integer divisions with an invariant dividend and monotonically increasing divisors. So in the innermost loop, the most innermost loop, we can vectorize by using the vectorizing compiler. So let me look at the performance results. So for performance evaluation, we compared the execution times of multiple 64-bit unsigned integer divisions using the following four implementations. So first one is the implementation using the 64-bit unsigned integer division instruction, DIV, of the Intel 64 architecture. The second one is the implementation of the proposed algorithm using the Intel 64 architecture instructions without DIV instruction. And the third one is the implementation using the intrinsic function, so which divides packed 64-bit unsigned integers in the Intel short vector math library, SVML. The last one is the implementation of the proposed algorithm using the Intel AVX 512 instructions. So this is the evaluation settings. So the batch size n of the 64-bit unsigned integer divisions varies from 128 to 124. So the dividend A is set to be a random number in the range from 0 to 2 to the 64 minus 1. And we note that the dividend and dividers satisfy the condition of theorem 1. So each batch of 64-bit unsigned integer divisions was executed 1 million times. And the number of 64-bit unsigned integer divisions per second MOPS value was calculated based on the average elapsed time. And we use the Intel Platinum 8368 processor. And the compiler option is following. So this table shows the performance of multiple 64-bit unsigned integer divisions with an invariant dividend and monotonically increasing divisors. So we can see from this graph table, so the proposed algorithm is faster than the Intel 64 DIV instruction and Intel SVML respectively. And when the batch size is 1024, the proposed algorithm is about 1.49 and 1.76 times faster than the 64-bit unsigned integer division instruction and the Intel SVML. So this is because that the Ice Lake microarchitecture of the Intel Xeon Platinum processor requires significantly fewer cycles of the Intel 64 architecture integer division, DIV, than the previous Intel microarchitectures, such as the Skylake microarchitectures. So the difference in performance between the proposed algorithm and the 64-bit unsigned integer division instruction is not so large on the Intel Xeon Platinum processor, but the previous Skylake architecture, so the proposed algorithm effectively reduced the execution time for integer divisions. So finally, I will conclude this presentation. So we proposed an algorithm for multiple integer divisions with an invariant dividend and monotonically increasing or decreasing divisors. So in such multiple integer divisions, we showed that if the dividend and divisor satisfy a certain condition, then if only one quotient is calculated by division first, the remaining quotient can be obtained by correcting the previously calculated quotient at most once. And finally, performance results shows that the proposed algorithm is faster than the 64-bit unsigned integer division instruction of the Intel 64 architecture and Intel short vector math libraries. That's all. Thank you very much for your kind attention.
very much. Takahashi.
Yes.
Yes, please.
Yes.
Thank you
Yeah.
for the talk.
Yes.
And I want to know because in my research, I usually obtain large systems of equations that we need to solve in an iterative way.
Yeah.
But we always have the same problem
Yeah.
that the resource are tends to zero.
Yeah. Yeah.
This methodology is well to apply to this.
I think it's possible if the such condition is satisfied.
So, okay, I need to try. I need to try.
But this condition is very tight. So the because the C means the increment
But
value.
only integers.
Yeah.
Not real.
Yeah, not real.
Oh.
Not real. So
I think that I need to think about because I'm not sure if it will be integer. Anyway, do you know Tuan from your university? Tuan? Tuan? Who is a professor.
I'm a professor of the
Yeah.
University of Tsukuba, Japan, nearby Tokyo Metropolitan area.
She asked about the Cornelius view.
Ah,
Tuan Pung.
Tuampu.
Because my research group works sometimes with him.
So which department of him?
Tuan Pung department. Computer mathematics.
Mathematics. I'm not sure about that.
Okay, no worries.
But you mentioned that he is belonging with the University of Tsukuba.
Yes,
Okay.
it's
Okay.
University.
Okay. Thank you very much.
Just a second, Mr. Takahashi, to
yeah.
check the chat. Maybe there is a question for you. And the question, the virtual room, because we have also a virtual room. This is a hybrid conference.
Yeah.
Yes. So we have to check a little bit the chat.
So
if there are some questions about you.
Yes, I cannot check the. Could you please
Thank you. Thank you.
check the?
What does
These are not referred
To another.
It was for the first presentation, for our first presenter. That was for you. So this is Ms. Herrera, and she will present her work. Okay, we will give you
Is-
the.
Okay.
the
There are no
questions.
questions.
So there is no question, just messages.
Okay. Okay.
Thank you very much. So now I am happy to call our last presenter. Okay, is Mr. Thomas Bujas.
Yes.
Bujas. Because this in Deutsch it's umlaut. So the U is U, but in your language?
It's like long.
Oh, long U. Okay, please. Large-scale study of binary galaxy image classification and impacts of image recommendation techniques. Thank you.
It's already shared, right?
Sure, yes.
Okay. And I'll start. So, hello, I'm Thomas Mužas. I'll be representing our study that I've done together with Andres and Tadas. We are all from the Vilnius University in Lithuania. So before going deeper into the presentation, I'd like to give you some context about what I'll be talking about. And so for this presentation, for my study, two major galaxy types are relevant. So the spiral ones, like you usually imagine galaxies, and the boring ones, the elliptical ones, which just are around and don't have any special features. The second very important concept that is relevant to this research is the redshift. And the scientific definition is the decrease in the frequency of the light emitted by the galaxy as it travels throughout the space. But basically, the further the galaxy is away from us, the bigger the redshift. And here's the visualization of how the redshift looks like. And in this paper, the higher the redshift value, the further the galaxy is considered to be. It's not always true, but for this paper, we assume this fact. And the further the galaxy is away from us or from the telescope, it doesn't really matter at those scales. The less features can be observed, or in other words, the quality of the image is poorer. So what problems are we trying to tackle? So there are quite a lot of studies done in galaxy classification, at least in the context of binary classification. And the authors have achieved great or even near perfect results, as you can see, 95, 99% of accuracy. However, there are some problems with the researchers. The first one is that they have limited their data set to low redshift values and sometimes used expert classified data sets or both, which actually implies a better image quality, making it a bit easier to classify those galaxies. And then the second problem is that it's quite difficult to compare the studies between each other because everyone uses different metrics. So, for example, some papers use cross-validation, others use the simpler training validation split. And then the other thing is that in some papers only accuracy is provided, and in other papers some combination of other metrics is provided as well. And finally, the other key point of my research is that other authors use augmentation techniques, which are there is a group of common augmentation techniques which I'll present later, but none of them, except only one paper, study its impact on the metrics. So what we were trying to do is two things. So first of all, to provide baseline metrics and provide the default, the standard metrics of machine learning, like precision recall, in this case through negative rate, because I care about both classes in the same amount, and the F1 score. And the important thing is that we are using a large, reliable, and diverse data set. And the second aim is to study the impact of augmentation techniques, which are quite frequently used by the other authors. So talking about the data that I used, I collected it from two projects. From two volunteer projects. They were presented an image of a galaxy and asked a couple up to, I guess, 15 questions, just visual answers. And based on those answers, the final classification was provided. So Galaxy Zoo 1, the first iteration, collected about 670,000 classifications into three classes, so spiral, elliptical, and uncertain. And Galaxy Zoo 2 collected about 240,000 classifications into 14 different classes or subclasses in this case. Then the goal of mine was to collect reliable galaxies, only reliably classified galaxies. So for Galaxy Zoo 1, it was pretty easy to filter them out because all I needed to do was to filter out the uncertain, the galaxies with uncertain class. And as you can see, it's removed approximately 70% of the data set. and only 250,000 galaxies were considered reliably classified. For Galaxy Zoo 2, it was a bit different because there were two flags present, the smooth or features. So smooth is for elliptical and features is for spiral galaxy. And there was such a possibility that both of the flags were present. So in this case, it was not considered reliable. Then a few galaxies were filtered out as artifacts. And in total, approximately 150,000 galaxies were kept from this data set. And finally, since both of them came from the same SDSS observation, the duplicate galaxies were merged based on their ID. And the important thing is that if classes did not agree on both data sets, and it happened, then they were removed as well. So the final data set size was 316,000 galaxies. Now let's talk a bit about the diversity compared to other authors. So in this case, redshift is denoted as the letter Z. And as you can see, there was one research by Cheng and others which used quite a broad redshift range, but they chose a very small data set. And other authors restricted their redshift range up to 0.1 and used also quite smaller data sets. And in our case, we not only used the broader redshift range, but also the biggest amount of galaxies. And also, since Galaxy Zoo 2 project, Galaxy Zoo 1 project, sorry, did not apply redshift constraints, so there were some outliers in that respect, and not to artificially increase our redshift range, I don't know, to 4, which is quite outlandish. We applied the 3 sigma rule to just narrow it to 0.28, pretty much. Then the images were gathered using the Sky server image cutout service, and then it was cropped in the center and rescaled to 128 by 128 pixels, and they were later on normalized. So now about models, about the training. So in this study, we've used 4 different architectures. So the first one is pretty classical, the ResNet 50. Then 2 architectures by Dieleman and Kavanagh, which are pretty similar, actually. And this C2 architecture is just an improvement of Dieleman architecture, and we used our artificial model, which was based on those 2 architectures, just to test whether what happens if the model is guaranteed to overfit. Yes. Now the other important aspect is augmentations. So pretty much all the papers that are studying galaxy classification use those augmentation techniques. So rotation by a whole number of degrees, then horizontal vertical flip, zooming in, then we've also tried random noise, and we've tried 2 different noise-based augmentation techniques that were not explored yet. And the first one I'll be referring to as the background noise, and the one on the right will be referred to as the center noise. And of course, it's exaggerated just to be better seen in the presentation. And all the augmentations could have been applied independently with a probability of 50% for each image during the training. So for the training process and to make our results comparable and reliable, we used tenfold cross-validation. We had some restrictions due to the usage of TPU, and that's why the test batch is so small. The maximum of 500 epochs was used, and we stopped early if loss didn't improve for 10 epochs. And as I mentioned, we'll be trying to present all the standard metrics along with the true negative rate. So in my study, I had quite a lot of like long and big tables comparing the results. So I'd like to present the maybe the most noteworthy results. And in this case, the first table is about the simplified, the smaller model that we tried, which is but pretty much guaranteed to underfit. So I've denoted like if the average result decreased in red and if it's improved in green. And in the parentheses, you can see the standard deviation of the metrics. So for the simplified model, pretty much all of the metrics just didn't change at all using with or without augmentations. And the standard deviation improved just a little bit, but nothing really important happened here. So essentially, none of the metrics changed by a statistically significant amount, since the model was underfitting. However, we had some more interesting results, and the most highlighting results were achieved by the ResNet 50, and I chose to show you 3 metrics. So as you can see, all of the metrics, not only the average like accuracy, true negative rate, and F1 score improved, but also their standard deviation improved. So first of all, 2 augmentation like groups that provided the best results were the standard augmentation, which is rotation, zoom, and both of the flips. So as you can see, for example, it decreased the standard deviation of accuracy by a half, and standard deviation of true negative rate by 3 times approximately. And then the second group that helped to stabilize models even more was adding random noise. So as you can see, the standard deviation for accuracy decreased by 5 times, for true negative rate by 7 times, and for F1 score even by 9 times. So the conclusions were drawn using the largest data set of reliably classified galaxies to date. And it is concluded that using standard augmentation, rotation, horizontal and vertical flip, and zoom improves accuracy and F1 scores by a statistically significant amount. And for the ResNet, the accuracy improved from 93.5% to 95.2%, and F1 score from 88.6% to 91.8%. The second conclusion is that adding random noise on top of the standard augmentation greatly stabilizes the performance of the models, and as I mentioned, it can improve stability with the standard by reducing standard deviation by up to 9 times in case of F1 score for ResNet 50. And then the third conclusion is that none of the augmentation techniques improve precision recall and true negative rate by a statistically significant amount. So this comes from all the models, and we didn't notice any significant improvement in those metrics. And finally, none of the augmentation techniques have any effect if a model is underfitting, in the case of simplified model. So that was what I wanted to talk about, and maybe some questions.
Thank you very much, Mr. Lucius, for a very interesting presentation. So maybe Elon Musk satellite can help you in your research somehow.
I'm hoping to work with this new data at some point, but
yes, I think all the scientific committee has great expectations from this. And we have to check a little bit room. Do we have any questions here? Actually, I would like to thank you all for your excellent performance and cooperation. And we have to just to check only.
No, there are no questions online. No questions.
No questions? So we continue on the room on 11. Always the session, the session, the second phase of the day begins at 11. So I think that we have a coffee time, so we can have a break.
I will present at 11 a.m. Yeah, this is my file.
So you will be the first one
Yeah,
at 11.
yeah.
Okay. You need to tell me how to pronounce your name because I am sure I will say it wrong. Okay.
Sure.
Thank you.
So it's just the one file.
Okay. There's a problem with this drive. Scan the drive and now fix it. Okay. Fine.
Yeah.
Maybe we do a second folder.
A second
Yes,
one.
in order not to.
I was doing the second chat. I'll do a second one.
Or inside.
Yeah, I was
Inside.
doing
Yes,
inside
yes,
for the
inside.
second section. So we
Perfect.
have first and second. My God, it's different from the Italian. Ooh.
That is in room F.
Room F.
Yes, it's the one. Maybe it's
Please open the
Yes.
chat room.
Okay. I took the PDF because it's easier than the PowerPoint. I took the file PDF, the PDF.
The PDF, yeah.
Because with the PowerPoint we cannot make the widescreen.
Yeah.
So it's
Is it okay? A PDF?
yes,
yeah,
perfect. The
okay.
PDF is perfect.
Okay.
Okay,
Thank you.
you're welcome.
Hi, how are you?
So, good morning, everyone. Are there anyone online? Okay.
Hi, I'm here.
Hi, good morning. So, I think that we can start the second part of this morning. Good morning. And
Good morning.
I'll present Mr. Chu. Yeah, right. And I'll share his presentation and I leave the stage to you. Okay. Please. Thank you.
Okay, hello everyone. Thank you for being here. Wow, there are so many people here. Thank you, and I'm happy and honored to be here with you and today. And before we begin, let me introduce myself briefly. I am Hyunbon Cho, and I'm co-author of this paper. And I am working in Samsung Display in Korea as a computer simulation engineer. Okay, so what I'm going to talk about is simulation model for reliability issues in OLED fabrication. The title is a prediction model of a pixel shrinkage failure using multiphysics in OLED manufacturing process. Here, and do you know OLED? Just call me OLED. As you know, an OLED means an organic light emitting diode. It's kind of an LED. It's also it's a film of organic compound. Therefore, an OLED display works without backplane because it emits own visible light. So this is the biggest great point and different point than LCD display. And also, and Samsung, and OLED display is a representative of display product in the world. And also, a Samsung display is the world's best OLED display product company. Yeah, right. Okay, this is table of contents, and I will divide my presentation into four steps from introduction to conclusions. And this presentation will focus on simulation method, right? First is introduction. First of all, I will introduce development of OLED display and recently. First, and high-end displays. Modern displays is required in high performance and versatile design. For instance, high performance are brightness and image quality and power consumption and so on. And new form factors are foldable and slidable and rollable and under display and camera, even automotive. So prediction, especially based on simulation, is very significant in design steps. And also, it obviously needs large in size and high resolution. Second, new challenges in display. As you can see the images, how many experienced of them? You are maybe you are iPhone user. No problem. Do you know that the panel of iPhone is made by in Samsung display, and over the past decade, and display technology is required high power efficiency and low power consumption. So we have to product to large in size and high resolution. Okay, let's talk about simulation methods. Yeah, first of all, I hope you understand about pixel shrinkage defect, and this slide will help you for understanding about pixel shrinkage. It's just called P-SK. However, I'm gonna use on both words for convenience. And as you can see, this image and reduction of luminous area is caused by progressive erosion of electrode in the pixel. So we call the pixel shrinkage. Therefore, we can divide the two parts as a location of water source. First, inside of panel is caused by on panel, which means there is a moisture absorption in the organic layer during its process. And second, outside of panel is caused by outside condition, which means there is a penetration level of water to whole part or dead space in edge part. So we can define the pixel shrinkage like this. So the mechanism of pixel shrinkage are internal outgassing and external penetration of water. I will explain pixel shrinkage in detail. And okay, for lifespan increase of the panel is very important. High area ratio and high open ratio in the pixel for unit area. So therefore, nowadays process architecture is very complicated by new form factor technology, and also there is an increase of penetration of water in organic layer. So it comes about and shrink or a decrease of luminous area due to cathode oxidation. So I think you enough understand about pixel shrinkage. And next slide. This is the main three physics of this simulation model. First, fixed law of diffusion. There is a fixed second law. It means, as you know, unsteady state condition to solve on as time steps, and change of concentration is linear related to twice a partial difference equation between and concentration allocation. And next, then Arrhenius equation is a calculation of diffusion coefficient as temperature. It's a crucial point. And last, WVTR, which means water vapor transmission rate. It's a calculation of penetration level of water. So we can get WVTR information from material company or open source. Therefore, our simulation model was set up based on these physics. However, we cannot all kinds of parameter information. So we got and we derived the unknown parameters as numerical coefficient as general. Next, simulation parameters. As I said before, pixel shrinkage defect is kind of reliability defect. So we cannot find this defect under process. we just find this defect after mass production, just like in the market. So prediction is very, very important. And also, and to improve the prediction accuracy, we have to consider all kinds of parameters, not only layer parameters for design and process information for process. For instance, layer parameters are horizontal layout and vertical process architecture, and process information are for equipment, for temperature, and thermal heat treatment. Okay. Yeah, next slide is introduced to examples. We can use two types of simulation model, case by case. First, in case of, as I said before, in case of outside cause, we can use a two-dimensional simulation model like a rise image. And also, in case of inside cause, we have to three-dimensional simulation model like this. Yeah, I will explain in case of 3D simulation model. I will explain in detail in next slide. This is process factors of P-SK. This is reliability issues. So prediction accuracy is very, very important, as I said. So we applied both factors which are design and process. So we got new index is equal to design factors multiplied by process factors. Here, process factors are heat treatment, cleaning, curing, and cooling buffer time. As you can see, the table 1, it's important that higher temperature and longer process time is effective factors to reduce P-SK. And also in table, cooling buffer time is also effective parameters in down pixel shrinkage. This slide shows a computational method. Our simulation process are 5 steps. First, 3DS layout to transfer 3D geometry, and second, and calculation of cooling rate for organic layer, and third, cleaning and heat treatment, and fourth, moisture absorption during cooling buffer. Lastly, moisture diffusion on the organic layer. And below these graphs are based on measuring data. As you can see, these graphs, we can understand process time and high temperature is very crucial factor to curing rate. And also in graph B, there is a drastic curve. So temperature is a very effective parameter to curing factors. Yeah, okay, right. And among these 5 steps, and I will explain in detail the 4 and 3 third steps and curing and even. And next slide. This contour is a distribution of residual moisture concentration in organic layers, and we can understand process time is effective to residual moisture like graph B between after cleaning and after oven. Below this graph, we got a function to quantity organic material water inflow during cooling buffer. Let's talk about simulation result, especially focus on simulation accuracy, as I said before. Yeah, this graph, yeah. And we checked and whether pixel shrinkage is true or not on 20 models and 20 evaluation data, like this bar graph. And the analysis of the result, we can predict an index, and we got high accuracy, like an R square is 96%. Therefore, we can provide the best and the optimal process conditions as simulation. And also hereafter, we will provide the specific platform for end user engineer, if not simulation engineer. Okay, last. In conclusion, we proposed the simulation model so they can predict pixel shrinkage caused by residual moisture in the organic layers. To improve accuracy of prediction model, we applied both factors, the design factors and process factors using multiphysics. So we got very high accuracy about R-square 96% based on 20 evaluation data. Therefore, we can provide the process window using this model. So when a new product needs to develop, this simulation model will be able to contribute to saving time and cost. Okay, thank you for your attention.
Thank you.
Yeah.
So thank you, Mr. Chu, for your presentation. It was really enlightening also for me, because I know nothing about all this stuff. I'm a river planner, so
Yeah.
but it was all very clear, so thank you. Are there any questions from the audience and also from the virtual room? Are there any questions? So I think that we can thank you again.
Yeah,
and
thank you very much.
So I think that the next presenter will be online, but I can see him in the virtual room. So I think that we can skip to the third, which is Mr. Claudio. Hi, good morning and welcome.
Hi, good morning.
So if you can share your screen so that we can see your presentation.
Yes.
Thank you.
It's okay?
Yeah, we can see the presentation.
Okay. So I can start?
Sorry?
I can start to speak?
Yes, of course you can start.
Okay, thank you.
Thank you.
So good morning for everyone. Thank you for introducing me. I am Claudio Shepke from Federal University of Pampa. The other authors of this paper are Marcelli Luca, also from Unipampa. And we have also the Gabriela Lopes Trindade from Pontifical Catholic University of Rio Grande do Sul, and João Plínio Yurger Neto from Federal University of Rio Grande do Sul. All these universities are located in extreme south of Brazil. Gabriel developed this part of this work in his master thesis here in Federal University of Pampa. This work has also Brazilian support from CNPq and CAPES. So we can see that many engineering problems are challenging or impossible to solve with classic mathematical optimization methods. This occurs due to the difficulty in formulating the modeling or the mathematical effort required to solve it, because the equations are not linear, non-differentiable, or discontinuous. Choose bio-inspired algorithms based on populations are widely used to solve this type of problem. So the objective of this paper is to solve and to modify the classical differential evolution algorithm, and we have proposed a little modification in this algorithm, and we search to find if these modifications are better to solve specifically economic load dispatch problems. And what is an economic load dispatch problem? For example, we have this kind of problem when we can see a distributed energy production, like here in Brazil. We have a continental land, and okay, your energy is clean. We can see here in these graphics we have hydrics, wind, biomass, solar. It gives us, for example, 90% of energy. However, this is not constant. We need rain, we need wind, we need sun, and in some moments, like we can see here in 2021, we have many rain. We need to use petroleum or natural gas or externally coal to produce this energy. The question is when, why, and what's the best price, what's the best moment to do this, and the impact in the nature. And because we cannot have 100% of time all the moment to clean energy, because this we need to use in other extreme times, other fonts. So the question is when and what's the best price for do this, so we can investigate this using optimization heuristics. And in other words, in mathematical words, we can speak that economic load dispatch has the objective to reduce the demand among the generating units to minimize the cost of the production this energy in our case, but the same problem can be used in other objectives and other problems. This power it's not generated by only one thermal font, but it's the result for a sum of the total of the system that we can produce. We have also losses with the transmission of this energy, and each unit has some limits in terms of productions. So if we consider these limits, we can reduce the number of units in production, but there are a limit of production in each case, because this we have also other effects. For example, this valve points, we cannot start a system and stop the system all the time. This gives us this ripple effect, as you can see here in the graphic, because it's good if we image the production that this system continues produce energy for us. We can also see in this problem that we have prohibited zones, that is the limits of the systems. If we use the maximal, we cannot extrapolate this maximal. We have also a distributed system in many regions of the land. Another concept that we have is the ramp limits, the restriction of operate range of our units. Do the force to operate continuous between two adjacent specific operations. So, Star and Price proposed the differential evolution algorithm. This algorithm is based on the process of natural selection of a space. We have an input. The input are the distributed production, and the output is the best solution that we found in the industry. The energy is in production. There are picos of consumption, and the operator need to decide if he need to start a system or stop a system, and this can be made using these algorithms. The algorithm is based then in select some individuals from the populations. We can make some mutations and percentage of these populations. As in the genetic, we have also crossover with mutations of some solutions, and in each step we evaluated this new generation and performed the update of the population conjunction. And then we replaced the old population with these new populations. There are many ideas as we can use the mutation process. Here are some examples of operations. We can also simulate the crossover effects, considering, for example, a binomial approach or an exponential approach. And for our new algorithm, we propose only to change the population. What we need, we update this population, but we not eliminate the original population. We include these new populations to have a more initial population to evaluate in the next steps of the process. We provide a MATLAB code. We test this in a simple computational node with extremely low memory. And in the tests, we consider for this paper, for these presentations, using only 15 generation units of energy. And we show the classic economic load dispatch of the non-convex load dispatch. For this problem, for the distributed energy, we consider for the modified differential evolution and for the classical differential evolution these parameters from mutation and crossover. This was also found in other algorithms like Santos, and the stop criterion was relative to the percentage of error in the last 15 iterations. That is, if the solution was not better than 10 times -6, we stop the execution. And we provide 20 executions for the first initial population. And these populations was randomly generated. In the results, we can see that the sum of costs for this classical data set for this 15 unit generations, we have found for the modified versions a small better solutions than the classical differential evolution. Here in this paper we not shows, but we have also made tests with larger problems and the solutions increase more. But for this paper we only test these 15 unit productions. And we also compare these results with other classical algorithms like the ABC. This is based on beans, and the classical also PSO, swarm optimizations algorithms, and our results are better as this other worked found in these papers. For the non-convex problem, we test also the same parameters as previous we show and discuss, and in this case we have a small but better solution than the classical differential evolution method. And also we compare these algorithms with other algorithms found in the literature. We can see here the PSO, genetic algorithms, SCA, swarm algorithms, and ABC. And in all cases, our proposed are better than the classical and good algorithms found in other papers. So, for this problem, low economic dispatch, our modification in the differential evolutions, we have better solutions. In terms of processing, we have also a reduction in terms of computational time. And in practical results, we found better results than that we found in other papers. To future works, we will extend these tests and put these tests not in a set of data, but also use this in real cases. And we also can provide an hybrid modification of this differential evolution with other algorithms. That's also a technique used in this kind of algorithms. So, thank you for your attention.
So thank you so much for your presentation. It was very nice and clear. And now I'm gonna ask if there are some questions from the audience and also from the virtual room.
So just clarification that I didn't get.
Okay.
I would ask if the computational time, because I didn't see which is the computational time taken by the evolutionary algorithm, the differential evolution algorithm, in comparison with a traditional, for example, generic algorithm. You say that you reduced 98% of time, computational time, but I didn't get in practice which is this time.
Okay, I understand. I can you respond because I work in also in parallel computing, and in the many kinds of problems that we have in this area, we are interested in time reduction. That's why I feel it's an interest for me, and I agree it's not interesting for other people. It's only for me.
Okay, thank you. Any questions? I think that there are no more questions, so I thank you again for your presentation. Thank you.
Okay, thank you.
So we now have the next speaker, which is Sue Arizona Herrera Taipe. Are you here? I read your messages about the video, but I don't have the video, so I don't know if you are gonna present.
Okay.
You're going. Okay. Thank you. You can start whenever you want. Thank you.
Okay. Good morning to all participants in this event. My name is Steve Harrison Herrera Taipe. I'm going to talk about an evaluation of direct and indirect memory accesses in Fluid Flow Simulator. I am a PhD student at the National Laboratory of Scientific Computing located in Brazil. This project has the collaboration of researchers from the National Laboratory of Scientific Computing and Federal University of Sao Paulo. Today, I'm going to talk about introduction, software architecture, experiments, conclusion, and future works. The mathematical model for three-dimensional two-phase flow, water and oil, is composed of a system of partial differential equation. This equation describes the displacement of the oil influenced by the water, and the other equation describes the velocity fields of fluids. This system of partial differential equation is solved using the AMPAES methodology, implicit in pressure, explicit in saturation. The transport modules is solved using the numerical method of finite volumes, and the other velocity modules is solved using numerical finite element methods. And this methodology can be visualized in the following graph. In this image, we can visualize the exchange of information between the velocity module and the transport module and this is where the data exchange with an indirect access structure take place. The graphical representation of the algorithm implemented in the simulator is illustrated in the following image. This image illustrates all the steps in the simulator, from the configuration of parameters and loops to solving the numerical methods for the transport and velocity modules. On this slide, this figure represents an oil reservoir, and when we perform computer simulation, we build a submodel. This submodel is used to perform to computer simulation. And in this step where we choose a data structure, this data structure is related to the computational mesh, can be a structured mesh and unstructured mesh. An oil reservoir can be modeled using a structured Cartesian mesh and unstructured meshes with tetrahedral, hexahedral, polyhedral, and other types. Advantage and disadvantage when choosing the mesh. When we choose a structured grid, the control volumes can be accessed using the identifiers A, J, K, and neighboring cells are located in this position. I-1, JK, I+1, JK, and others. Unstructured meshes best represents complex geometries and additional require structures to locate the neighbor control volumes. For example, neighbor connectivity matrix or neighbor connectivity list. In this image, we can visualize the additional structure called the neighbor matrix, where to update the information, it is necessary to use the neighbor matrix to locate the data that are dispersed in memory. The numerical method using this indirect access data structure is presented in the following slide. In this algorithm, we have a single loop traversing all controls volumes, and indirect data access occurs in this point. We are thinking of developing a scalable simulator and more complex oil reservoir can be modeled by refining the mesh. We are working with regular meshes, and in this case, we can eliminate the indirect access considering a three-dimensional mesh. This strategy increases the computational operations and data allocations, but is solved with the computational power of a supercomputer. In this slide, we present the algorithm using a direct access data structure. In this scenario, we have three loops that go through the dimensions of the matrix. And it is not necessary to use this additional structure called matrix neighbors. All the experiments that I will present were performed on two Intel architectures on the Santos Dumont supercomputer. The first architecture is Intel Xeon Ivy Bridge and Intel Xeon Cascade Gold. The Ivy architecture has 256 kibibytes per core and 2.5 megabytes in last level cache. And the Cascade Lake architecture has 1 megabyte per core and 1.375 megabytes per core on shared memory in last level cache. For more details, see the following link from Intel. And in the following image, we collected the simulator execution time using 1 to 4 computational nodes with 150 MPI process. We have 4 images illustrating the times collected using the direct and indirect access structure. The yellow and blue illustrates the numerical simulator execution time with an indirect access data structure. and the green and red line illustrates the numerical simulator execution type time with an direct access data structure. A single Santos Dumont compute node with a Ivy bridge architecture has 24 computer cores per CPU, and a single Santos Dumont computer node with a cascade architecture has 48 computer cores, 24 per CPU. This is an explanation of why the lines in this image are not linear. The best runtime is on the Cascade Lake architecture implemented with a direct access data structure. In order to explain the reason for the performance improvement, we performed an analysis of cache miss, cache hit, and last level cache in memory hierarchies of the Santos Dumont supercomputer. This table provides instruction for collecting hardware events using Intel tools. Cache miss is when information requested by the CPU is not found in the cache memory, and cache hit is when information requested by the CPU is found in cache memory. On this slide, we present a table with the information collected and a comparison between them. Results displayed are for 10 MPI processes. This same analysis was extended and performed for 10, 24, 48, 96, and 150 MPI processes. On the next slide, we illustrate the bar chart with all results. This is cache miss in L1. This is the bar chart cache miss in L2. And this is the bar chart cache miss in last level cache. This image illustrates the cache reduction in last level cache. Conclusions and future works. With the experiment presents and the result collected, we can say it was possible to reduce cache miss using a direct access data structure. For future work, we will use adaptive MPI to improve communication between MPI process. We will use vectorization instruction by Intel. We will improve access to data in the matrix using the matrix black box algorithms. We are going to carry out new experiments on different architecture, such as, for example, Army architecture. Thanks to the National Scientific Computing Laboratory for providing HPC resource for the Santos Dumont supercomputer. And I would like to thank the Coordination for the Improvement of Higher Education Personnel CAPES in Brazil. Thanks for question, please write me in my email.
Okay, thank you for your very specific presentation. So, are there any questions from the audience and also from the virtual room? So,
okay, thank you.
I'm surprised that the direct method of access the memory presents good solutions in the architecture, because I know this problem that is indirect access. We need to select a data structure and then another, and to find the neighbor points. And in your case, you show that the indirect methods can have also good solutions for the use of unstructured match. I'm surprised with your results.
Thank you. So if there are no more questions, I think that we can thank you again, Mr. Edison Herrera, and go ahead with our schedule. But are there anyone online that are going to present? Mr. Carlos Collasos with the review of nuclear thermal propulsion analysis of fuel element and simulation methods. Are you online? I don't think so. And also Mireia Zapata and Luis Felipe Tipan with the paper called Design and Implementation of Wind Power Charging System to Improve Electric Motorcycle Autonomy. So, I don't know. There's anyone. So, I think that we can make a break, and I'll be here if one of the next presenters is gonna show online. So I think we can take a break. Thank you.